Thin film design usually requires some experience in finding good solutions. If you use genetic algorithms, you can eventually do it without any experience. Actually, the algorithm promises that it finds solutions that you could never think of. I tried a little bit to work with genetic algorithms, and I implemented a tool called GenetiCode, which is an add-on to code. And for some types of problems, it works really nicely. So I will like to show you some examples in this tutorial. I start with motivation. Basically, I describe the type of problem that you can solve with GenetiCode. And I give you a first simple design problem where we can watch basically how the solution is made in real time. I will explain you then how genetics really works, how we can get solutions by an evolutionary algorithm. And after some simple real-time demonstrations, I show you some results in the case of advanced examples, which take a little longer. And here I will just show you the results at the end of this talk. This is a typical inline coater for a large area applications. For example, you have glass panes coming in, and you have several stations where you can deposit thin films. Basically, each station is equipped with one cathode or a group of cathodes, and they can produce materials. For example, a silicon target will be used to deposit silicon dioxide. Concerning the equipment, you have some restrictions of the thicknesses that you can produce. Basically, the cycle time, that means the time between one pane and the next, gives some restriction, and the power of the cathodes and so on. So usually for every station you have a choice of different materials that you could produce there, and for each material you have a thickness range that you can produce in one of these stations. So now the question is, you have a given problem, you want a coating for a certain technical application. What cathode groups do you have to use after each other in order to produce this coating that solves the problem, that is a good technical solution for the given problem? This type of problem can be addressed with GenetiCode. So actually you know how many deposition steps you can have in your deposition machinery. You know what materials you could produce in each station, but you don't know what is the best sequence and what are the thicknesses that you should use. That is what GenetiCode can do for you. It can find out the sequence of materials and the best thickness values. And I will just show you a very, very simple introductory example. That's a problem that has been, I guess, addressed the first time in the 70s of the last century. Actually, in a situation like this, you probably want a heatable windshield. So you would like to have a window that you can look through if everything is fine. But if it's cold like this, you want to de-ice the window. So you want to be able to heat it. So what you are looking for basically is a piece of glass which can have some electrical conductivity. Obviously, glass cannot do that by itself. So you need a coating. And here in this case, I propose a 3-layer coating on glass that provides some electrical heating, some current that you can pass through it. And so actually the quantitative description of this problem is, we want a certain sheet resistance. Suppose we need a value of 2.2 as a target, and we want visible light transmittance. We want to look through this piece of glass as good as possible. Our wish here is the best you can have. That's 100% transmission. And now if you take a look at the coating, and you vary like you do that in code easily, you can have all the thicknesses as sliders here. So you can check the thicknesses. You can instantly see what kind of sheet resistance and transmittance we would have. And then in code, you know, you have a kind of deviation, fit deviation, which measures the difference between the target values and the current values. And here the difference is the value of the sheet resistance minus the target value of the sheet resistance. That's this value here. You square that. You can have some weight. In this case, 1/10 of this number should be added to the difference, the squared difference of visible light transmittance and the target value of 100. That's the total fit deviation as you usually have it in thin film design in code. In genetic algorithms, usually people prefer a number called fitness, which is large if the solution is good, in contrast to the deviation, which is small if the solution is good. And I have chosen this combination, 1 divided by a small number plus this deviation. So if the deviation gets smaller and smaller, this number gets bigger and bigger. So this measures the fitness of the coating, and as you see, if I vary this here, the fitness depends on my choice of the thicknesses, and obviously we are looking for a coating with the highest fitness. Let's do it the genetic way. How do we proceed? First, we need genes. That means we need to describe a coating as a sequence of zeros and ones in this case, like genes that computers like, just with 2 states, zeros and ones. And my choice was the following. We take a 4-byte floating point number, so that represents the floating point number by a 64-bit, and let's call this number G, and then you can take this formula here. You take the absolute value of G, add 1, divide by that, and then you have a maximum number of available materials for your coating devices, in this case 7, and then you take this, you truncate this floating point number that you will get here to get an integer number between 1 and 7. So that's what you do, and whenever you draw a random floating point number G, you will get one choice of materials. So these 64 bits here represent the choice of material, and you do something similar for the thickness. You take another 64-bit floating point number, this time called F. You take this combination, and then you get one thickness out of this range of the minimum thickness and the maximum thickness that you can produce for this given material on this side. So if you draw a number G, you select the material. If you draw a number F, you select the thickness for that material. So if you combine these two 64-bit numbers, you get 128 bits, and these are the genes for one layer of your coating. If you have n layers, n deposition steps, then you have n times 122 8 bits, representing the total layer stack. So these are the genes, and now you can do evolution. In evolution, you do the following. First you generate many of those coatings by just drawing random numbers for all the genes, and this is called a population. Usually you have a few hundred coatings in a population. You can also take more or less, but typically, let's say a few hundred. They have random genes. So now you go through all these layer stacks, you compute their fitness, and then you sort the population. Then you go to the this is the starting generation, basically the starting of the evolution, and then you go to a next generation by applying some rules. You take the best individuals, those on top of this list, and they go without any modification to the next generation. So the next generation can never be worse. It can only improve compared to the previous one. With all the individuals, you do what's called mating. You select two as parents. They interchange their genes, and you build new children which have mixed properties of the two parents. And in order to follow the rule survival of the fittest, you take those with higher probability, those parents which have a high score, which have a high fitness. So they get more likely new children. So the majority of new children are children of really the best parents. Then in addition, you add some thunder and lightning. Some of the genes are exchanged randomly. That's called mutation. So you add some random modifications of the genes. Usually they are not very good, but sometimes you generate some surprise, and one of the children is a kind of genius that is solving the problem of finding the best coating, to a high degree. So then, when you have the next generation, you do the ranking again. You go back, you sort the population, and you do this many times. So this way, you hope that you find better and better solutions. And then in the end, when you have a certain number of generations generated newly, then you take this as the end of the evolution, and you take the best individual as the best result for the given problem. I will show you some examples that sometimes it makes sense to do a refinement to improve this best solution even more by some manual adjustments. I will explain that in a moment. Okay, let's take a live example. The given problem here of the heatable window is really very simple. So I can show you results in real time, and I have prepared a GenetiCode configuration that solves this problem. Let's do it first with a single layer. Actually, I have prepared a few materials that are available, some oxides and nitrides and some metals. So what you see here is basically you will see the number of the sheet resistance and the visible light transmittance. And our goal is to have a high transmission in the visible and low sheet resistance. That means high infrared reflectance. Here we see the infrared reflectance between, I guess, 3 microns and 20 microns wavelengths, and here that's the visible light range where we want to see through the window. Actually, I can just start the evolution. In this case, the problem is really simple. It will be very quick, and but also not very good. The winner is a layer of copper, about 7.5 nanometers or 8 nanometers. Let's see how this goes. The light transmittance is something like 60%, and the sheet resistance is 2.6. That's the best solution, but as I said, not very good. So let's try 2 layers. And if we start the evolution, now the genetic algorithm will go through several iterations, and it will probably find a much better solution. At least the visible light transmittance here is now much higher, almost 80%. Sheet resistance, well, that's the next generation. I do the genetic algorithm twice in order to see what are the best solutions, and I think in both cases we will see more or less the same solution. So that was the evolution for the two-layer system already. We can here cycle through the solutions. The fitness was 16.7 in run 1, and that proposes to use almost 18 nanometers silver and 21 nanometers titanium dioxide. Run 2 is actually the same solution. So both evolutions have resulted in the same two-layer stack. Let's do it for 3 layers. And let's start the evolution, and you will see here probably, hopefully, that different choices of different materials are taken. Obviously, the one with silver in the middle is best, although there could be other materials in this solution. And we are now in the first evolution. The fitness is much higher as before. It's 97. So we can get closer to a good solution here with 3 layers instead of 2, much closer. Here the evolution now takes some steps, does some kind of new inventions, and let's see what it found. The highest fitness is this one, or this is even higher. So this is a quite good solution using 2 titanium dioxide layers of almost the same thickness with a silver layer enclosed in between. So that's a very good solution without any thinking. We just told the program, take the best materials that you can find to solve this problem. And it did. It found a very good solution in a very short time, actually. Let's go to a different climate and let's discuss a different problem. Here, if you live in the desert of Arizona, you have many hot days over the year with full sunshine, and in the summer that means very high temperatures and high air condition bills. And some people got the idea that if we could have a coating on these large roofs that you usually have, that would cool the building without any electric bill by passive cooling. That would be very nice, and there are some proposals by a group of the Stanford University that you could actually achieve that, and they tried that it works, and they claim that it works, and I thought, well, that's a good task for GenetiCode. So let's take a closer look at this problem. Actually, you have, as I said, a lot of sunshine. Here in black, you see the spectral distribution of the sunlight that arrives on Earth. Between 300 nanometers roughly and 2,500, there's a lot of sunshine. And suppose you have a coating on a large glass pane here. You can compute the absorption of this system here as 1 minus reflectance minus transmittance. And well, obviously what you have to do if you want to do some cooling, you have to absorb as the absorption should be as low as possible, almost zero. So we have to find a coating which absorbs almost no sunlight, although there is a lot of sunlight shining on your roof. So usually we have to try to do that by a high reflectivity. So the coating should be very reflective in the visible. And then we have a cooling mechanism by radiating black body radiation. If you have a hot roof, maybe it has 330 Kelvin or 300 Kelvin, let's stick to almost room temperature. Then you have black body emission in the infrared, and the transmission through the atmosphere works nicely here in this area, where you have a kind of gate into the open space. So you can send energy to the stars. Here you have some transmission of the atmosphere. There's also a little bit of transmission here, but not very much radiation emitted by this hot roof. So, but here you can use this channel to radiate into open space, if there are no clouds in the sky, of course, which is true in Arizona for the most days of the year. So if the sky is free of clouds, you can send infrared radiation into the space and it never comes back. So you have a cooling power if you emit more into space than you absorb. So let's see how we can do that. Actually, a candidate for, in my example here, is coating on glass. And I have visible and infrared properties of the following materials: silver, gold, copper, and then I have silicon oxide, titanium dioxide, and silicon carbide. For all these materials, I have properties in a large spectral range. And well, let's suppose now, that's an interesting question. We are going to start the genetic algorithm. We tell GenetiCode just optimize this coating, and you can easily find a very good solution. And now the question to be addressed is, who is going to be the patent holder? And that's not so easy, because no person does an invention. That question is really difficult. Well, obviously the laptop that does this work in the next 5 minutes cannot be a patent holder legally. The person who pointed out the problem, well, that would be maybe me. Okay, I can be the patent holder if you like, but maybe not. The programmer of the software, that would be me too. Or those people who invented genetic algorithms, those could be the patent holders. So that's really open, and let's not be blocked by this question, but I just wanted to point out that many of the inventions in the past, many coating inventions, can now be invented by GenetiCode in a few minutes without any input from my side, except having written this algorithm. Okay, let's take a live demonstration again. For this problem, I load a passive cooling with 3 layers, and I start the evolution. And while it runs, I will show you here what it does. I compute here in the list of integral quantities and code the solar absorption. And you can see here in this solution it's 7%. Here it's 3% or 4%. I compute the absorbed power, assuming a certain high power illumination by the sun. So in this case, the absorbed power is about 40 watts per square meters. And I compute as a third quantity the emitted power, the infrared power that goes through this window of the atmosphere into open space. And then I compute the difference between emitted power and absorbed power, and that's the cooling power, the net flow of energy. So indeed, you can find coatings on glass which cool a roof with a certain power during the day of full sunshine in Arizona. So that could really work, and as you will see, the cooling power is not too bad. Actually, we are going through a cycle where there is almost no improvement in this fitness, The cooling power is not really very high, 26. I think we had a larger value already in the first evolution. Let's wait a little bit longer. I think the next run starts now. Here, this is the report about the progress, first generation and the third run, second. So now we have already 36 watts. And obviously what you need, you can see that here in the proposed layer stack, you need a thick silver layer on glass, and then on top of that you need oxides. And I have allowed very thick layers for this purpose. So the oxides should be thick enough so that the emissivity here is high enough. What you see here actually basically is the vibrational modes of the oxides. They take care of the absorption or the emission, so to speak. And what we found here already is a cooling power of more than 40 watts, which is not too bad. Okay, I guess if you think in terms of solar cells, with 1 square meter you will get something like maybe 120 watts. They have an efficiency of typically 10 to 12 to 14%. So if you would have an electric power of 100 watts per square meters or 120 watts, and you would drive a refrigerator or the air condition inside, maybe the cooling power would not be much higher than this. Okay, in this case, the best solution was in run 1, the 3.1. That means 43 watts per square meters. And actually, I have found better solutions with 5 layers, but I don't want to spend too much time here in order to find those solutions of about 60 watts per square meters. And actually here in my talk I have a very simple solution, which is the best with the highest number that I found up to now, and that is actually a thin float glass layer, a thin layer of about 42 microns. And you can buy glass of that thickness, rollable glass actually, so you could use that, put it on, coat it with silver and put it on float glass, and then you would have a cooling power of 85 watts per square meter, which is really very nice and could efficiently cool a building. Well, let's see if at some day systems like this will be really used to cool cars or our buildings. Okay, let's go to some other examples which are a little bit more advanced, involving more layers and which take longer, which I cannot show you in real time. I address some typical problems of thin film design. Let's start here with an edge filter on glass, where you want a high transmission for some colors, for wavelengths, let's say up to 550, and then the transmission should go down to 0 for let's say red light, orange, and red light. So the red curve here, that's the target spectrum, and we are looking for a coating on glass that does it. Here, that's a good solution, or not really a good solution, but one solution that I found for 10 layers on glass with the genetic algorithm that I described to you. Well, actually, you might think that you need more layers, and this is the best solution that I was able to obtain within a few minutes or hours, I guess, for 20 layers. And you see, especially here in this area where you need to block radiation efficiently to 0, the algorithm has difficulties to get nice zeros. So that seems to be difficult for the genetic algorithm, but I thought a little bit about it, and I found a good solution to overcome this limitation. So we can help the algorithm a little bit by taking a short look in a textbook. And in order to produce zero transmittance, actually you should produce very high reflectance in this range, and you can get very high reflectance by a so-called Bragg reflector. So I thought it would be a good idea to tell the program already we have a Bragg reflector, so two layers with low and high refractive index that repeat 20 times. So we can use this building block and tell the genetic algorithm, let's work with 6 layers called A, B, C, D, E, F in this case, but the 2 in the middle, they are repeated 20 times. So now we still have a small number of layers, namely 6, but 2 of them are repeated 20 times. So actually we have 24 layers in this solution. And since we give already this structure to the genetic algorithm, it's much easier to produce the zero transmission here. And in fact, this was the best layer stack after maybe 1 hour of iteration, or half an hour. Still, you can see some wiggles here, so the curve in transmission is not so nice. And what I thought would be useful now to get rid of these substructures here is to do a refinement, a manual refinement of this coating. And what I did, I took those 24 layers and then I fitted them individually, every thickness, without changing the materials anymore, but I selected all these 24 layer thicknesses in code as a fit parameter, and then I fitted just the thicknesses with a downhill simplex algorithm, like you do in code anyway. So after this manual refinement, I could get a quite nice solution. So the transmission here is not 100%, but much higher than 90%. And the few percent here are the reflectance of the backside of the glass, where I have no anti-reflection coating, so we have 4% from the backside which just come back and are missing here in transmission on this side. So this is actually a nice solution. Actually, I was not right with the number of layers. I think I mentioned 24, but it's 44. 20 times 2 is 40. Sorry. So we have 44 single layers, and in this case now 44 thicknesses optimized. And this gives a quite smooth transmission curve, except for this for this sharp edge. Okay, another example is a bandpass filter, where I have helped the genetic algorithm again by assuming we are using 2 Bragg reflectors. Here, this one and this one. Each one is a double layer repeated 15 times. So let's do the math now. That would be 60 layers. And we have 1 layer on top, a so-called cavity layer in between, in the middle, and 1 below. So we have 63 layers all together. And after a while, the genetic algorithm found this solution, again with some structures which are not really optimal. I did the manual adjustment again and found a very nice solution for this bandpass filter. And this also just by helping the algorithm a little bit by using these Bragg reflectors. But I can assure you I'm not an expert in thin film coating design for optical filters. So this is really a coating made by GenetiCode just with a little bit of help. Final example is this one. Here I had the task to develop coating on glass which reproduces in its transmission the sensitivity of the human eye. Obviously, this was used to produce a detector which looks at radiation like the human eye does. And the blue curve here was the target curve, and the dotted line here. That's what I achieved with 16 layers, also with refinement, and that's also a nice solution, which would be hard to obtain by manual trying. So, in conclusion, I would like to summarize that genetic algorithms are really suitable for automatic coating design. Sometimes they need to be pushed a little bit by some knowledge that we put into it, but it should be some basic knowledge, not real expert knowledge. And what remains if you use genetic algorithms still is the main problem. You have to define the problem. You have to carefully define the problem, and then you just let the algorithm run. Sometimes it takes overnight, but if you are lucky, before breakfast the next morning, you have the solution of your problem and you can sleep well in between.